If you are operating in the cloud today, and let's be honest, who isn't? You know that data isn't just important.
Oh, it's everything.
It is the currency. It's the lifeblood of every single application, every transaction, every bit of IP your organization is building. But when we talk about, protecting that data, we often bring this baggage from the past with us.
Right, yeah.
We think about tape drives, these massive dedicated physical backup servers, managing these super complex proprietary software licenses. And frankly, those traditional methods are, well, they're not just obsolete in the cloud. They actively work against the agility and the cost efficiency that AWS is supposed to give you in the first place.
Oh, that's the real problem. Data protection has to evolve. It can't be this manually managed IT task anymore. It has to become, an automated governed policy. And that's really the heart of the challenge, isn't it? How do you handle, say, dozens of AWS accounts running hundreds of different resources, EC2, RDS, S3, DynamoDB?
All with different compliance rules.
Exactly. All with different rules, and you have to make sure every single thing is protected, it's auditable, and it's secure without needing this, army of engineers to constantly babysit a bunch of fragmented snapshot scripts.
And that is precisely our mission for this deep dive. We are putting on our solutions architect hats, diving straight into the source material, and we're going to give you a complete masterclass on AWS Backup. This is not just about, clicking a button in the console. This is about architectural resilience.
The goal here is to give you the shortcut. We want you to walk away from this really understanding the core technical architecture, the high security stuff like immutable vaults, and, this is critical, the cost implications of doing centralized automated backup management at massive scale, across your entire organization's AWS footprint.
Okay, so let's start with the simplest possible definition of the tech we're talking about. AWS Backup. How would you sum it up?
I think the best way to put it is it's a fully managed policy-based service. Its whole job is to centralize and automate data protection across a ton of different AWS services.
And before this was a thing, it was, fragmentation was just the norm, right?
Oh, it was the Wild West. We were all running around solving the exact same problem in 50 different ways. You'd have these really complex Lambda scripts tied to CloudWatch events just to trigger an EBS snapshot.
Or, I remember this, you'd have scheduled cron jobs running on some poor EC2 instance just to dump SQL databases.
Yes. Or you were relying on these little bespoke service-specific rules you built directly into EFS or RDS. Every service was its own little island of protection policy.
I remember those days so clearly. It was just a fragmented, messy landscape, and the weakest link was always human error.
Always.
If a developer forgot to set up that one specific cron job after they migrated a database, that critical piece of data was just unprotected, maybe for days or even weeks.
And AWS Backup just gets rid of that chaos. It unifies that entire landscape into that, that coveted single pane of glass for data protection. And the scope is really what makes it revolutionary. We're talking about centralized management for EC2, for RDS, EFS, DynamoDB, S3, even Aurora databases.
And it even reaches on-prem, which is still kind of mind-blowing to me.
It is. You can even manage your existing on-premise VMware workloads if you hook them up through the AWS Storage Gateway. That kind of breadth, managed from one single console, just completely changes the game for audits.
Okay, now let's drill down into a technology contrast, because I think this is really fundamental to understanding why it's so scalable. We mentioned the legacy systems, the Commvaults, the Veritases of the world. They traditionally require you to install this heavy agent inside the server's operating system.
Right. And that agent has to do everything. It's reading the file system, handling compression, managing deduplication. It's constantly eating up CPU and memory.
And managing that agent across a fleet of servers becomes this massive operational overhead.
And this is where AWS Backup gives you what we call the agentless advantage. In, I would say, the vast majority of use cases, AWS Backup doesn't need to install anything inside your guest OS. It operates natively. It talks directly to the AWS control plane. So when you ask for a backup, it doesn't log into your server.
It's not SSHing in.
No. It just sends an API call to the underlying AWS infrastructure, the EC2 service, the RDS service, and just says, hey, initiate your native snapshot capability for this specific resource.
So it's not really a backup product in the traditional sense, where it's reading bytes and copying them one by one. It's more of a coordination product.
Precisely. That's the perfect word for it. It's an orchestrator, a policy engine that drives the native platform capabilities that are already there. And this control plane-driven approach means it's infinitely more scalable. You're just managing policies and API calls, not dealing with software compatibility or agent versions or CPU overhead on thousands of individual servers.
The shift.
Yeah, that shift from managing physical software installation to just managing policy, that is the defining feature of cloud-native backup.
Okay, let's pop the hood on that. Let's unpack that coordination or orchestration concept, because I think a lot of listeners might still be picturing, copying files.
Yeah.
So, section 1, the technical mechanics. How does this central orchestrator actually get the job done?
Well, when you look at the source material, Chapter 2 really breaks it down. The core idea is that AWS Backup is the conductor. It's the intelligence layer. So when you define a backup plan, let's say for an EC2 instance that's backed by an EBS volume AWS Backup, just translates that policy into the right sequence of API calls. It calls the EC2 service, which then internally does the actual snapshot process.
Okay, so if I set a policy that says, back up my production RDS database daily, AWS Backup just makes a call to the RDS API and says, create a snapshot for DB instance X.
Correct. And that's a huge strength because it's leveraging the service's own native optimization. RDS snapshots are already designed to be super efficient for databases.
And EBS snapshots for block storage.
Exactly. DynamoDB backups are optimized for distributed NoSQL tables. AWS Backup isn't trying to reinvent the wheel for each service. It's just making sure the right wheel is turning at exactly the right time, according to your schedule and your retention policy.
This brings us right to a crucial technical point: the difference between block-level and file-level operations. Can you clarify why AWS Backup operating at the block level is such a massive advantage?
Yeah, it all boils down to efficiency and speed, especially when you're dealing with terabytes of data. A traditional file-level backup tool, it has to read the entire file tree. I mean, it has to walk through every single directory, check all the metadata, compare modification dates, and figure out which individual files have changed.
That sounds incredibly slow if you have millions of tiny files.
It's a huge resource hog. Block-level backup, which is what EBS snapshots use, works completely differently. It operates at the physical disk level. It doesn't care about files or directories. It only tracks which discrete blocks of data on the disk have been physically modified since the last backup was taken.
So let me see if I've got this right. If I change just 3 lines in a huge, say, 10 gigabyte file, a file-level backup might have to reprocess that whole 10 gig file. But a block-level backup only captures the few kilobytes of blocks that contain those 3 lines of text.
Exactly right. It's so much more granular and faster for big data sets because you skip all that overhead of walking the file system. For EBS specifically, AWS Backup triggers those block-level incremental snapshots. And for RDS and Aurora, it manages their native database and cluster snapshots, which are also highly optimized.
And this is where it really feels like magic to me, the whole incremental backup process. You said it only copies the change blocks after that first full backup.
Yeah.
But when I need to restore, I don't have to go and manually figure out this whole chain of incrementals I need to apply. That sounds like a monumental improvement.
It is, hands down, the single biggest operational relief that this architecture provides. In the old systems, managing those chains of incremental or differential backups was a super common cause of failure.
Oh, yeah. If one link in that chain was corrupt, the whole thing was useless.
The whole restore failed. The elegance of the AWS system is that every single recovery point, even if that point only represents, say, 5 gigs of changed data, it acts like a full standalone backup when you go to restore. AWS just abstracts away all that complexity. When you kick off a restore, the system instantly calculates and compiles the necessary block map. It stitches together the base full backup and all the required incremental blocks to give you a complete, coherent data set for that specific point in time.
So I just pick the date and time, and the system delivers the data. It completely hides that messy incremental chain under the hood.
Yep. It completely masks the complexity.
That has to slash the recovery time objective, the RTO, right?
Yeah.
Because you're not spending hours trying to validate a backup chain anymore.
Absolutely. The RTO shifts. It's no longer dependent on validating some fragile chain. It's now just dependent on how fast you can provision the new resource.
Okay, so let's talk about where this data actually lives. If I create 1,000 snapshots across all these services, I know it's in the cloud, but is it just sitting in one of my normal S3 buckets?
That's a super common point of confusion. The underlying storage backend for these native snapshots is, in fact, Amazon S3. But, and this is a big but, this data is stored in what we call a service-managed S3 bucket.
What does service managed actually mean in practice?
It means 2 critical things.
Yeah.
First, Those recovery points are not visible or accessible through your standard S3 console. You can't just go browse the internal structure of your backups using normal S3 API calls.
Okay, so they're hidden.
They're hidden, and second, this is the security feature. These backups are controlled exclusively through the AWS Backup console, or the console of the resource itself, like the EC2 console for EBS snapshots. This separation makes sure that an attacker or even a rogue employee who's messing with your standard S3 policies can't accidentally or maliciously delete your recovery points. It provides this essential layer of integrity.
That centralization of control, where the policy lives and where the data is managed, that really feels like the foundation of the high security strategy we're going to get into later. It all ties together.
It does. It's all part of the same design philosophy.
Okay, moving into section 2. Let's talk about the policy structure itself. To deploy this effectively, you really have to understand the components. What are the 4 conceptual pillars that define the AWS backup architecture?
Right. Chapter 3 in the source material outlines this really well. And understanding these 4 pillars, plans, rules, vaults, and assignments, is the difference between just using the service and, architecting a real enterprise solution. The first pillar is the backup plan. This is your master policy document. You can think of it as answering the big questions like, what is our overall protection strategy? Or what's the template for our most valuable data?
And then inside that plan, you have the backup rules, which is the second pillar. So a single plan can have multiple rules for different needs.
Exactly. You might have a plan called regulatory compliant protection, but inside that plan, you have one rule for operational recovery. Let's call it the daily rule, that keeps data warm and ready for 30 days. And then you have a second rule, the archival rule, that moves the data to cold storage and mandates a 7-year retention period. The rules define the nitty-gritty, the frequency, the retention, and the lifecycle actions.
Okay, third pillar, backup vaults. These are the logical containers for the recovery points that those rules generate. Why is the vault so important? It sounds like more than just a storage bucket.
The vault is where all your security and encryption lives. This is where you define the KMS key that's used to encrypt the recovery points. And, crucially, the vault is where you define the access control policies, dictating who can see, restore, or delete the data inside. And as we'll discuss, the vault lock feature makes it the most secure boundary in the whole system.
And that brings us to the fourth and final pillar, the resource assignments. This is how you define what resources get covered by this plan. And you mentioned before, the best practice here is all about tags.
Standardized tagging is absolutely non-negotiable for large-scale management. I mean, manually listing out resource IDs just doesn't scale. You want to define dynamic assignments. You tell the plan, include any EC2 instance, any RDS database, or any EFS volume that had the tag compliance PCI. This decouples the protection policy from the resource lifecycle itself.
So as soon as a developer tags a new resource with compliance PCI, it's just automatically protected. No one has to do anything else.
It's automatically protected. It makes the system resilient to how fast you deploy.
But before we get to deployment, what are the initial setup steps? It's not totally zero config, is it?
That's right. There are 2 essential hurdles to clear first. The first one is service opt-in. AWS is pretty cautious about protecting resources that might not need it, or, resources that have unique cost profiles. So you have to explicitly go into the AWS backup settings and opt in to protect specific services like S3, DynamoDB, or VMware. It's a way of making sure you acknowledge the potential cost and complexity.
And the second prerequisite?
The second is IAM roles and permissions. AWS Backup needs permission to act on your behalf across all these other services. Now, the default AWS Backup default service role often works just fine, but if you're using custom encryption keys, especially for sensitive EBS volumes encrypted with your own KMS key, you have to confirm that the IAM role has explicit columns decrypt and columns encrypt permissions for that specific key.
That sounds like a classic gotcha.
It's a very common one. If that linkage is missing, you might complete the backup successfully, but then find out months later during a crisis that the restore fails because the service role can't decrypt the data.
Oof. Okay, let's pivot to backup modes. Moving into Chapter 4, we need to dissect the crucial differences in how the data gets captured. We've got scheduled versus continuous, and then that critical consistency debate.
The scheduled versus continuous question really defines your RPO, your recovery point objective, basically. How much data are you willing to lose? Scheduled backups are discrete points in time. If you back up every night at 2 a.m., your maximum potential data loss is almost 24 hours. They're simple to understand and manage, and they create these distinct snapshots.
But continuous backup, or point-in-time recovery PITR, That fundamentally changes the RPO equation, doesn't it?
Yeah.
Especially for high transaction services like RDS or S3. How does that mechanism actually work differently from a snapshot?
Yeah, PITR is a different beast. It requires the underlying service to be able to continuously stream its transactional logs. So think of it less like a snapshot and more like a high-speed log recorder that's just running constantly. For RDS, this means it's tracking every commit, every transaction, every schema change. This constant log stream, combined with an initial full snapshot, lets the system virtually rewind to any second within the retention window, which is typically up to 35 days.
Wow. So if I have a critical failure at 10.47 and 35 seconds in the morning, I can specify my restore point as 10.47.34 a.m., and the system uses the base snapshot plus all those logs to reconstruct the state of the database exactly 1 second before it all went wrong.
That's the power of PITR, that granularity. It's perfect for operational recovery because it minimizes your data loss down to seconds.
There has to be a cost trade-off there.
Oh, absolutely. It's important to note the cost. Maintaining that constant log stream for 35 days, keeping it hot and ready for instant access, is inherently more expensive than taking a scheduled snapshot that you can move to cold storage after a few days. You're paying a premium for the operational readiness of those continuous logs.
Okay, let's shift to the consistency question. Crash consistent versus application consistent. Why does this matter so much, particularly for databases?
A crash-consistent snapshot, which is the default for a running EC2 volume, is a simple point-in-time capture of the disk. It guarantees all your disk blocks are safely stored. But it's crash-consistent because any transactions that were being held in the server's memory and RAM that hadn't been written to disk yet are just gone.
For a simple web server, this is usually fine. The OS just recovers.
But if I'm running something like SQL Server on that EC2 instance, I absolutely cannot accept losing transactions that were mid-flight in memory.
Exactly. For databases running on EC2, which is a super common architecture, you need application consistent backup. This requires actually communicating with the application layer inside the OS to tell it, hey, pause transactions, flush all your pending data to the disk, wait for the disk snapshot to finish, and then you can resume. This process is called quiescence.
And this is where we finally hit that exception to the agent list rule. You need some help to achieve that quiescence. That is the crucial gotcha. To get application consistency on a Windows machine, AWS Backup needs to leverage the Volume Shadow Copy Service, or VSS. VSS is a native Windows feature that handles all that flushing and I/O freezing. And AWS Backup talks to VSS through the SSM agent, the systems manager agent that's installed on the EC2 instance.
So if I want a true application consistent snapshot of my Windows database server, the SSM agent has to be installed, has to be running, configured, and have the right permissions to talk to the VSS components. If SSM isn't there, I only get crash consistency.
That is the hard requirement. The SSM agent is the bridge that lets the control plane reach into the OS for a moment to coordinate that transaction pause. On Linux, it's a similar process, usually using file system freezing utilities like susfreeze, which also requires the SSM agent to coordinate the command.
So it's the one scenario where the control plane needs an on-instance agent to guarantee data integrity.
Right, because it needs to interact with the OS memory buffer, not just the underlying storage layer. This step definitely adds complexity, and it's a common failure point if SSM isn't managed robustly.
Understanding those nuances really moves us from just deployment to, true architectural strategy. So now let's talk scale. Section 3. Scaling and high security strategy. If I'm running a modern enterprise with lots of dev teams, maybe 50, 100, or even more AWS accounts, configuring a backup plan in every single one of those accounts is a total nightmare. It's audit chaos.
Oh, it is.
How do we enforce centralization?
You have to avoid decentralized management at all costs. It just leads to configuration drift, massive security holes, and guaranteed audit failures. The enterprise pattern, the established gold standard, is centralization using AWS organizations. What you do is you designate one specific AWS account. It should be clean, highly controlled. Maybe you call it the central backup management account. This one account becomes the single point of governance for all of your data protection policy.
Okay, so you have this one central account. How do you push that single governance policy down to the other 50 or so spoke accounts where the actual data lives?
You do it through backup policies applied within AWS organizations. You write a single JSON policy document, which is really just a set of instructions, and you apply that policy to the root of your organization, or maybe to specific organizational units, or OUS. That policy then automatically trickles down, it inherits, to every single member account under that structure.
So you could write a policy that says Every resource-tagged environment production must be backed up daily, retained for 90 days, and copied to Vault X.
Exactly. And the crucial element here is that the policy originates centrally, but it executes locally in each account. This ensures compliance without any manual work from the local account teams.
But the policy relies entirely on the developer, using the correct tags. What happens if a developer, just through an error or they forget, fails to tag a new database?
And that brings us back to why your tagging strategy is key. It has to be enforced organizationally. The solution isn't just hoping for good behavior, it's enforcing that behavior with other organization policies.
You're talking about service control policies or SCPs?
Yeah. Yes. SCPs are absolutely essential here. While a backup policy defines the backup action, an SCP is a guardrail that prevents users from doing things outside your security perimeter. You can use an SCP to explicitly deny the creation or modification of a resource if it does not include the mandatory backup plan tag.
Oh, that's clever.
Or you can do the reverse. You can use an SCP to deny the deletion of that tag once it's been applied to a production resource.
That's a brilliant application of policy layering. So I can't even launch a production EC2 instance without the backup plan, gold tag.
Yeah.
And if I later try to remove that tag to, say, bypass the backup fees, the SCP just denies the action.
It creates a self-healing, self-enforcing system. When developer tags a resource gold, it is protected immediately. If they try to get around the policy, they hit a hard technical barrier that's enforced at the organization level. It minimizes the risk of unprotected resources just slipping through the cracks.
Okay, now let's address the biggest modern threat. Ransomware, or even internal sabotage. We've enforced centralization. But if a sophisticated attacker gets into our production account, they could encrypt the live data and then just delete the local backups.
Right, they go for both.
We need resilience outside of that blast radius.
Yeah.
This is where cross-account copy becomes mandatory, right?
Then negotiable is the right word. Cross-account copy ensures your data is safe, even if there's a catastrophic account compromise. The strategy is to automatically duplicate your recovery points the moment they are created and send them to a secure, separate data bunker account. And the security model is all about isolation. That data bunker account should have IAM policies that make it a one-way street. The production account can write copies into the bunker,
But it can't delete.
but the production account should have absolutely zero permissions, no S3, delete object, no backup, delete recovery point in that data bunker. This effectively air-gaps the recovery point. Even if an attacker completely owns the production account, they can't reach across that account boundary and delete your immutable copies.
So the data lives in two places, and the policies make sure that the producer of the data can't destroy the reserve copy.
Precisely. It mitigates the risk of rogue admins, malicious automation, and sophisticated ransomware that targets both your primary and secondary storage at the same time.
And this leads us to the final, ultimate layer of defense. The concrete bunker around the data itself. AWS Backup Vault Lock, which is detailed in Chapter 6. This is the feature that stops an attacker who does somehow manage to get into the data bunker account.
Vault Lock is the absolute strongest security control in the entire service. It transitions your recovery points from just being secure to being truly immutable. And we need to be clear about what that means technically. Vault Lock enforces worm compliance. Write once, read many. A standard vault lets you delete things based on IAM permissions. Vault Lock just overrides IAM permissions by enforcing a legal retention policy.
And the distinction between the two modes is crucial. Let's focus on compliance mode.
Compliance mode is the gold standard for ransomware defense. When you enable Vault Lock in compliance mode, you set a minimum and a maximum retention period. Once that lock is finalized, and there's usually a short cool-off period to prevent you from accidentally locking it forever, that policy is absolute. The source material is very clear on this. Once it's locked in compliance mode, no one, not the account root user, not the most powerful IAM role you can create, not even AWS support, can delete those recovery points until the defined retention period has expired.
If your compliance demands 7 years, that backup is staying for 7 years.
7 years, period.
I think we have to reiterate the inherent risk of that power, though. It's incredible for security, but the cost implications if you misconfigure it are terrifying. If you accidentally set a 100-year retention policy.
You are financially committed for a century. That is the trade-off. It provides the ultimate assurance against tampering, but it demands extreme caution when you configure it. It's the digital equivalent of an irrevocable legal contract. You're sacrificing flexibility for guaranteed integrity.
Is there a softer version?
There is. The alternative is governance mode. This is a softer approach you'd use when you need strong protection, but you might need some kind of administrative override, maybe for testing or some emergency maintenance. Governance mode lets specific, highly privileged users bypass the lock using special IAM permissions. But for true, regulatory, defensible protection against ransomware, compliance mode is the benchmark.
We've built a fortress. Now let's talk about the practical side of things and the economic levers. Moving to Section 4, Logistics, Restoration, and Case Studies. We established earlier that cost management is really dictated by lifecycle rules from Chapter 7. How do those rules actively save us money?
Lifecycle rules are the financial engine of your backup plan. After that initial recovery point is created, the lifecycle rule determines when that data transitions from expensive, high-performance warm storage to much, much cheaper cold storage, the archive tier, and then finally when it can be deleted.
Okay, so you keep it hot for a bit, then move it.
Right. If you need immediate operational recovery, you keep the data warm for, say, 30 days. After that window, the probability of you needing an instant restore drops dramatically. So you set the lifecycle rule to say, after 31 days, transition this recovery point to cold storage. That transition happens automatically, and your cost per gigabyte just plummets because you're accepting slower retrieval times if and when you need that data later for an audit or long-term compliance.
This feeds directly into our retention strategy, which is in Chapter 8. How should an organization think about structuring their retention periods?
We typically see 3 different retention strategies, and they're all defined by risk and regulation. First is operational recovery. This is short-term, maybe 7 to 30 days. It's focused on rolling back recent user mistakes, bad deployments, or minor corruption. You need high availability for these backups. Second is compliance. This is long-term, and it's driven by industry or government rules, IPK, GDPR, Sarbanes-Oxley. They might mandate that you keep transaction data or records for 1, 3, 5, even 7 years. This data is the primary target for cold storage.
And the third strategy, the legal hold. That's the mechanism that overrides the first 2 when a specific event happens, right?
Yes, the legal hold is absolutely critical in litigation or compliance investigations. If a company is facing a lawsuit, they're legally required to preserve specific data, regardless of what the automatic retention policy says. AWS Backup lets authorized people place a legal hold on specific recovery points, and that prevents them from expiring, even if the 7-year retention period passes. The hold has to be manually and explicitly released once the litigation is over. It's like an emergency stop on the garbage collection process.
Let's walk through the actual restore procedure. A critical database has failed. We need to recover. What is the sequence of events when I click Restore in the AWS Backup console?
The most important operational fact, and this often catches people new to the system, is that AWS Backup never performs an in-place overwrite or a rollback on the existing resource.
That's a deliberate safety measure.
It is, so it doesn't touch the broken thing.
It creates a new resource instead.
Exactly. It uses the recovery point to provision a brand new instance or a brand new volume. When you start the restore, the recovery point supplies the data, but you, the user, have to supply the environment. You have to specify. What EC2 instance type should this new server be? Which VPC and subnet should it launch into? What security groups should we apply? The backup only contains the raw block data. It doesn't contain all that environmental context.
So the final steps are validating the data on the new server, and then redirecting all the traffic.
Yep. You verify that the new server has the right data and the application state is good. Once you've verified it, you do the cutover, update your DNS, reassign the elastic IP, or shift your routing rules to point to the new healthy server. And the old failed resource is left intact for later forensic analysis if you need it.
Let's ground this in reality with a couple of case studies. Let's start with the large-scale EC2 protection from Chapter 9, that fintech organization managing high-volume data across 50 accounts.
Right. The challenge for them was just overwhelming. They had 1,000 EC2 instances, and the CISO was demanding proof that every single production database was protected within a specific RPO. The sheer volume of developer activity meant manual checks were completely impossible. So their solution was this multi-layered policy architecture. They used the central backup account strategy, managing everything from one place. But the most inventive part was using service control policies, SCPs, to prevent developers from deleting the critical backup plan tag on any resource that was designated as production.
That structural enforcement.
Yeah.
That's the difference between hoping for compliance and actually guaranteeing it.
It is. They made it so that if a production asset existed, it had the tag, and therefore it was automatically picked up by the centralized plan.
Yeah.
Then they combined that with mandatory cross-account copy to an immutable vault lock account.
And the outcome?
The key outcome was incredible. A database administrator accidentally terminated a critical server. Within minutes, the ops team saw the issue. Because the centralized policy had ensured a fresh snapshot was copied to the data bunker account just 4 hours earlier, they initiated the restore from that immutable, secure copy. The database was back online with minimal data loss in under 15 minutes. The success wasn't just the speed of the snapshot, but the guaranteed availability and immutability of that copy, which was protected from the very account that caused the failure.
That's resilience against human error and insider threat at the same time.
Wow.
Now let's look at the financial side in Chapter 10, the healthcare provider dealing with complex IPA requirements and a mix of resources like RDS and these massive EFS volumes.
Their number one requirement was 7-year retention for patient records. The challenge was that 7 years of high-performance RDS snapshots and especially terabytes of X-ray images stored in EFS would have bankrupted them if they kept all that in expensive warm storage. So their architectural solution was all about aggressive, intelligent tiering. They applied lifecycle rules strategically. For the EFS file systems, which had the bulk of the raw image data, they set up the rule. Keep it warm for 30 days, then transition to cold storage, the archive tier, for 6 years and 11 months.
And that transition to the archive tier, which is slow to get back, but incredibly cheap to store, that's where all the savings came from.
Precisely. For their highly transactional RDS data, they used continuous backup for 35 days, which gave them that crucial point-in-time recovery to the second, covering their high-frequency operational window. For the 6+ years of compliance they needed after those 35 days, they accepted less granular, scheduled snapshots that were also moved to cold storage.
And the result?
By moving all that voluminous EFS data and the long-term RDS snapshots to the cold tier, they met the 7-year high-pay compliance requirement while slashing their overall backup storage costs by over 60%. It's the perfect example of using the right tool tiering for the right job long-term compliance to get massive cost efficiencies.
That 60% saving is the sound of management sharing. But before anyone just goes and implements aggressive tiering, we need to talk about money in detail. Section 5, the cost equation and avoiding pitfalls. What are the two main cost drivers we have to track when we're using AWS Backup?
The cost model is pretty simple, fundamentally. It's based on two components, storage cost and restore cost. Storage cost is how much data you're keeping and which tier it's in, warm versus cold. Restore cost is the fee you incur when you pull data back, especially from cold storage where retrieval is infrequent, but it carries a specific fee.
Let's break down the calculation from Chapter 11 with that specific scenario. We've got 100 EC2 instances, 10 terabytes of total use data, running a daily backup, and we assume a 2% daily incremental change rate with a 1-month retention period, all in warm storage.
Okay, so we have to calculate the accumulation. The initial full backup is 10 terabytes. Assuming a typical warm storage rate of, say, 5 cents per gig per month, that initial backup alone costs you around $500. Now for the daily change. 2% of 10 terabytes is 200 gigs of new incremental data every single day. Over 30 days, you accumulate 6,000 gigabytes, or 6 terabytes, of incremental data.
So the total data stored in warm storage at the end of month 1 is 16 terabytes, the 10 terabyte base, plus the 6 terabytes of increments.
Correct. 16 terabytes in warm storage runs you approximately $819 per month. Now let's consider the impact of that lifecycle rule after 30 days. If we move that base 10 terabytes to cold storage, where the rate might be something like a penny per gig, that same 10 terabytes only costs about $100 per month.
The cost difference is just stark. Over $800 versus just over $100 for the bulk of that data. We should probably be clear about why cold storage is so much cheaper.
It's cheaper because you are accepting increased latency. Cold storage is highly optimized for archival density and low operating costs, but getting the data back takes time. We're talking hours instead of minutes. So if you restore from cold storage, you incur a retrieval charge and you have to wait. The key takeaway is absolute clarity. If your data doesn't require an RTO measured in minutes, aggressively moving it to cold storage with lifecycle rules is the single most effective way to manage your budget.
That transparency around cost is essential for any architect. Now, we've covered a lot of positive ground, but Chapter 12 details the technical gotchas. What are the small, overlooked details that consistently derail these enterprise deployments?
Two technical pitfalls are responsible for the vast majority of failures I've seen. First one, KMS key permissions. If you are encrypting your sensitive EBS volumes or EFS shares using a custom key in KMS, you have to remember that AWS Backup is a totally separate service. The AWS Backup IAM role must have explicit policies allowing it to use that custom key for both encryption during backup and decryption during restore. If those permissions are even slightly wrong, for example, if a key policy limits access, your backup job might succeed.
So you get a green check mark.
You get a green check mark, but the crucial restore job will fail when you need it most, and it will give you some cryptic access denied error.
So the developer thinks, oh, the backup ran fine last night. But the security constraint on the KMS key makes the data totally useless in a crisis.
Exactly. The integrity of that key policy is paramount. The second gotcha is much simpler. Region support. AWS services roll out new capabilities region by region. You must verify that your chosen target region supports the specific advanced features you need, like S3 continuous backup or item-level restore for DynamoDB, before you design a global deployment strategy.
Never assume parity across all regions.
Never assume.
And finally, monitoring and auditing. We can't just set this up and forget about it. How do we ensure we're continuously compliant?
You have to actively integrate with other AWS management tools. For immediate awareness of a failure, you configure AWS Backup to integrate with Amazon SNS, the simple notification service. You want an SNS topic that receives alerts specifically for any job status marked as failed. This pushes an alert immediately via email or to your on-call tools, making sure failures are addressed in minutes, not days.
And for the auditors?
For compliance, you use the built-in Backup Audit Manager. Auditors don't want to see a bunch of screenshots from the console, they want reports. Audit Manager provides automated, continuous compliance reports that prove your backup jobs are running successfully, your retention policies are being met, and that your recovery points are adhering to all the necessary security controls, like immutability. It's the essential tool for governance.
That covers the full life cycle, from architecture and policy creation, through security and centralized scaling, all the way down to cost control and continuous auditing. For our final thoughts, let's run through some rapid-fire FAQs drawn from Chapter 13. Question 1. Does AWS Backup stop my EC2 instance during the backup process?
No, it does not. It uses the native snapshot capability, which creates a crash-consistent snapshot while the instance is running. It ensures zero downtime for your application.
Question 2. Can I back up data from my on-premise servers into AWS Backup?
Yes, you can. You can use the AWS Storage Gateway for general on-prem file systems, or specifically for VMware environments, you can use the dedicated AWS Backup agent for VMware to capture those local workloads.
Question 3. Is AWS Backup region-specific?
Yes, by default it is. A vault in, say, Ireland only stores data locally in Ireland. For true disaster recovery across geographic areas, you have to explicitly configure and pay for cross-region copy within your backup plan.
Okay, question 4. Can I restore just a single file from an EC2 snapshot?
You can. You use the item-level restore feature. What this does is it creates a temporary mounted volume from the snapshot that you can browse just like a normal drive, and that lets you extract individual files or directories without having to restore the entire server.
And final question. What happens to my backups if I permanently delete the source EC2 instance?
The backups are independent. They will persist in the backup vault until their defined retention period expires. Deleting the source resource has no effect on the recovery points. You know what really stands out, connecting all these dots, from that orchestrator concept all the way to the worm-compliant vault lock, is the fundamental shift in operational philosophy. Data resilience is no longer about managing software. It's a policy decision that you manage centrally. It gives you unified policy enforcement, robust, defensible security, organization-wide scalability, and that granular, cost-optimized control through intelligent tiering.
So what does this all mean for you, the listener? We've detailed the architecture and the pitfalls.
We want to leave you with this final provocative thought, and it builds directly on the most essential advice in the source material. Don't wait for a disaster to learn your restore process. That is the moment of maximum stress, where tiny, unfamiliar technical steps can lead to catastrophic delays. Go create a test vault in your AWS console today, back up a single non-critical development resource, and perform a full restore procedure from start to finish. Document every single step. That hands-on familiarity is your single best tool for ensuring a rapid recovery when the pressure is truly on.